Hello, this is an example that deals with the sampling distribution of the sample mean. And it is an accompanying example that would also go along with the central limit theorem. If you recall, the central limit theorem basically says that if I have a random sample that is quote-unquote large enough or sufficiently large, your book uses n being greater than 30 as a large enough sample. But if I have a sample mean that is, or a sample size that's larger than 30, the sample mean, any sample mean that I draw from that population, that sample mean will be approximately normally distributed. So you'll need to review the central limit theorem and its implications before we kind of get into this example here. But in this example, suppose that cattle in a large herd have a mean of 1,152 pounds and a variance of 18,769. What is the chance that the mean weight of the sample steers would be greater than 1,159 pounds if 68 steers are sampled at random from the herd? So the idea here is we have this big herd of cows. And what I'm going to do is I'm going to let X be the weight of a cow. Okay. And from the information that I have here, that means that mu, the mean weight, is 1,152, and the variance of the weights are 18,769. Well, that means that the standard deviation, if you take the square root of this, you'll see that it's 137. Okay, so we had this population of cows. The average weight of all the cows is this value. This reflects the variability in the weights of all those cows. Now the question is, if we go out and get 68 of these cows, or 68 steers, what is the chance that the average weight of those 68 steers is greater than 1159? And so what we want is we want the probability that X bar is greater than 1,159 pounds if n equals 68. That's what we want. Okay? What's the chance of that happening? Okay, well, in order to compute a probability about any random variable, in this case the random variable is X bar, we have yet to observe X bar because we have yet to take a sample. But if we do go get 68 cows, what is the chance that the average weight of those cows is greater than 1,159 pounds? Okay, well, this is the random variable. In order to say something about a probability of a random variable, we need to know the distribution of this random variable. Okay, well, we don't know anything about the distribution of X. All we know is that X has a mean of 1152, and this is the standard deviation there, 137. So we can't get it from there, but we do know by the central limit theorem, X bar is approximately normal with, I'm going to come down here, with the mean mu sub X bar, the average of the sample averages is actually mu, so in this problem it would be 1,152, and the standard deviation of X bar, or also called, this is also called the standard error of X bar, that is sigma over the square root of n, and that equals 137 over the square root of 68. And if you do that computation, let me do that on the side here. Okay, so I had to go get my calculator. 137 divided by the square root of 68, and you get 16.6. So this is a reflection 16.6 is a reflection of the variability that X bar has from sample to sample. Okay, so what we know by the central limit theorem is that X bar is approximately normal with these parameters. The mean is 1152. The standard deviation of X bar is 16.6. Now I should go on to say here, let me complete this statement. By the central limit theorem, this is true because n is sufficiently large for us. It's greater than 30, right? N is 68. And so we're saying sufficiently large is greater than 30. That works out in this problem. Okay, so we know that X bar is approximately normal. So when we come back to this probability, this is what we want to compute from the beginning. The probability that X bar is greater than 1159 is, well, what do I have to do? If this thing is normal, I've got to standardize this in order to give me a probability in terms of the standard normal, or in terms of Z. Then I can use one of the normal tables and get that probability. So if you recall, off to the side here, the formula that we use to standardize something is to get a Z, we take a variable, subtract off the mean of that variable, and divide by the standard deviation of that variable. Okay, well, for this problem, our variable is X bar. The mean of X bar is mu sub X bar, divided by the standard deviation of X bar is sigma sub X bar. Okay, so I'm going to do that to the left-hand side of this inequality in here. So I've got the probability that X bar minus mu sub X bar over sigma sub X bar, that is greater than what I do to one side of the inequality, I've got to do to the other side of the inequality. Okay, and by the way, I'm not multiplying or dividing either side of the inequality by a negative number, so I don't have to worry about flipping this to a less than. It stays greater than. Okay, so I've got 1159. Now I subtract off mu sub X bar, and instead of writing the symbol mu sub X bar, I'm actually going to write the quantity, and that quantity here is 1152 divided by sigma sub X bar, that is 16.6. Okay, so now what I have here is this equals a probability. This now becomes a Z, a standard normal variable, and that's the probability that Z is greater than, let me do this computation here, 1159 minus 1152 equals 7. 7 divided by 16.6 is 0.42. Okay, so now I just need the probability that a standard normal variable is greater than 0.42. So this problem boils down to, on a side here, here's the picture of the standard normal distribution. Here I've got 0.42, and there is 0, and I want the area under the curve to the right of this point. Okay, that's what the probability is. Well, what I know, if you look in your table, if you look in table, let me see, I don't know if it's table A or table C. Hang on a second. If you look on table C, you'll notice that the area under the curve to the left of 0.42 is 0.6628. Okay, and so I'm gonna put the table here under the camera so you can see it. Here I'm looking at table C. My Z score is 0.42. That number 6628 is the area to the left of that Z score. Okay, so this is 0.6628. So this right here is 1 minus 0.6628. That shaded area is then 0.3372, and so then this probability is therefore 0.3372, and that is the answer here. Okay, that's kind of separate there. But so looking back at this problem, the question was, if we were to go out and take 68 steers, what's the chance the average weight of those 68 is greater than 1,159 pounds? Well, that chance is a little bit over a third. Okay, so pretty good chance here of this event happening. And in order to compute this probability, we had to know the distribution of x bar. Well, the central limit theorem tells me that x bar is approximately normal with these parameters here. Lastly, I do want to say that this probability, if I can get this in here, this probability is approximate because the distribution of x bar is approximate, right? We said by the central limit theorem the distribution of x bar is approximately normal, so any probability we get as a result of that is going to be approximate. And the approximation gets better and better as n, the sample size, gets bigger and bigger.